So I'm going to get started right away. So I'm going to talk a little bit about observability at Airbnb, because that's the team that I'm on. And then I'm going to talk about the trace reconstruction job that we've built, we call Upshot. And then some successes and failures that we've had along the way, especially as we scaled it up to accommodate most of the traffic at Airbnb. So start off observability at Airbnb. And what is Airbnb? Airbnb is a global community that offers end-to-end trips that include where you stay, who you meet, and what you do across the world. And so our accommodations market, which is kind of the most famous part of Airbnb, is 5 million listings in over 191 countries, 300 million guest arrivals. Beyond just the accommodations market, there's also the experiences market, where you can connect with locals who have interesting activities to do in your destination. And beyond that, there's also an integration with Resi, which offers high-quality restaurant reservations in a number of cities around the world. And so within Airbnb, I'm not working on the product side. This is Flink forward, after all. I'm working actually much deeper in the stack. And I work on the observability team. And what that means is I'm building tools for the engineers at Airbnb. The mission of the observability team is to ensure that software engineers at Airbnb have the monitoring and introspection tools to successfully operate and develop their services. And so that means that I'm building tools for engineers to understand and gather the data about their systems. And so to understand when things go wrong, and when things do go wrong, because inevitably they will, they have the tools to look at it and understand why they went wrong. And they have the data to do that. OK? And the reality is that there's a lot of tools out there to help do this. And so we integrate with many of them. Right? We integrate with third parties for metric stores, third parties for exception tracking, and run in-house versions of like Elasticsearch and Sentry and this sort of thing for exception tracking and logging and all these metrics use cases. And that's great. A lot of these tools are very high quality and they're very useful. But when things actually go wrong, the problem is that you then get overwhelmed. You have some alert fires because some traffic drops off. What should an engineer do? Should they go to the logs and see, like, oh, I don't recognize this logging? Or should they look at distributed tracing and say, OK, I see this request pattern across my entire service graph. This looks wrong. Should I go to exception tracking in Sentry and say, OK, this exception is new? And those are all the right choice for a certain engineer, for a certain service. But beyond that, say I have a runbook and I say, OK, go to your distributed trace, because that's probably, given this particular metric drop-off, that's probably where this is. And you include that in your alert message. When PagerDuty pages you on your phone and you get the SMS, you're just like, OK, I just need to log in and look at my distributed tracing tool. OK, now what? So this is a distributed trace. And what it means is there's some request at the top level, which is feeding down. And Thrawn is an in-house tool for RPC requests. You have RPC requests that go down into some other drop wizard service. And OK, that drop wizard service raised an error. That's why it's highlighted in red. Great. So I need to go find that error in my other tools. Well, that means that I need to have a way that actually link out and share context with these other tools. Also, I need to sample this data, because honestly, observability data, 99.9% of it is useless. That's kind of like an existential question of observability. It's like, I'm not processing transactions in finance systems and that sort of thing. Most of the data I collect is pretty useless. But that 0.1% is really important to understand what actually is happening and what's going wrong. But if I sample this request, and I don't sample the same thing in my exception tracking or in my logging, I can't actually tie these things together and get a coherent story of what's going on. Second thing is, I can get trapped where I send the data into one data store, say my exception tracker, or my logging system, or my metric tracker, and that data can kind of get trapped, where I don't get the opportunity to pull it out and join it with these other data sets. And that's, again, because of this volume problem. I have tons of data, and I want to just take the most important aggregates and samples of those data and keep them around. And so a lot of the time, it feels like, as an observability team, I really want to be able to pull that data back out, or at least be able to do something else with those data. But usually, it's piped directly into these other tools. Right? My logging stack goes directly into logging. My tracing stack goes directly into tracing. My metric stack goes directly into these metrics. And I don't have an opportunity ever to join them together. Reality 3 is that beyond that, picking which things are actually important is really hard. And this is actually a timing question. It's really an event time question. Because say this is my job graph, or my request graph. And I have some presentation service going down to enriching the data, which is going down to the actual data store, pulls it back up, and now my presentation service goes and validates that data. Well, what if that validation fails? I get an error, and that happens after I've pulled all this data up. Well, I'd like to know what actually happened in the enrichment and data store layers to be able to debug this. But if I'm doing something where I'm sampling early on in the request and I'm deciding whether to keep the data early, I kind of throw that away. And so like when something goes wrong, I want to tell the system, give me all the data and keep that piece of data. And so a lot of systems that actually manage these sorts of data, you have to make that decision up front. And we wanted to get away from that paradigm because rare things often are the most important things to actually catch. You know, if we have a host or a partner that works with us that gets a booking for one of our higher end pieces of property that's, you know, it's a $10,000 booking, and we decide that, and that one is an error, and we decide that we throw that away. That seems like a bad decision, right? Like, it's important to know why those things fail, and those rare things fail more often because they're not exercised as often. And so we really want to be able to make the decision to choose that data after the whole event has passed and after I kind of have this transient aggregate, okay? And so this is where things started to look more like a stream processing engine. And so the key points about this, in the observability team, we saw that we had a lot of places where it was hard to contextualize data. It was hard to understand what all the other pieces of data were. It was hard to reuse data and process it in different ways. And then, finally, it was hard to even choose the right data to keep, right? Because we don't want to keep all the data. That's expensive. But we do want to keep the right subset of data. And so this should look like a pretty standard graph of data. So we have a service process, we have instrumentation. The instrumentation includes tracing data, which is like each request that is made by a service. That's written out to a Kafka stream. A Flink job reads from that Kafka stream and writes it out to various data stores, right? So we write it out to Kafka, which then is read in by Druid. We write it out to some of our vendors who then present that as dashboards and as trace reconstructions and that sort of thing. And so Flink is kind of serving as this router that does this aggregation and decision making of what to keep, what to throw away. And this, I kid you not, is the actual job graph. This is much simpler than the previous job graph because the idea is much simpler, right? We thread a single trace ID through the entire request life cycle, right? So we have a single key that we're actually keying on. And so all we do is we read in the data, we rescale out so that we can do some more complex pre-processing on the individual events. By the way, if you don't use rescale when you're trying to actually do pre-processing of stuff before you do a join, it's actually really handy, reduces the network cost a lot because you're only going out to a subset of the downstream subtasks. Then you have a key by and a process function that we call collect trace. I weeded out a lot of operators that get chained together here just so you can kind of see the main point. But this is actually the structure of the subtasks, of the tasks themselves. And with this, the main complication was when we first implemented this, we used a session window because that's kind of the natural form of, OK, I don't know when this request will end. I'm just going to key by the trace ID. I'm going to take a session window until enough time has passed, and then that'll be fine. The problem is that if you actually do that, you end up creating a lot of timers. And that actually becomes a performance issue as you try to scale up. And so I'm going to walk through a simple example of what we actually do instead. And so we basically have a really poor man's session window. When we receive the first event, we say, how long, at most, are we willing to wait until this entire request completes in event time? We set a timer though, and then we keep collecting more trace events. And then eventually we're going to receive something that we know is the end, or at least we think is the end, because that was the top level request or top level job or something like that that finishes, right? And so something actually made the call into our infrastructure, or something triggered this asynchronous job that is running. And so I know that eventually that thing should complete. At that point, I can set a much more aggressive timeout and fire off and aggregate that entire set of events early, okay? And that has main benefit is that reduces the amount of state that we actually have to store. We can still allow for very long requests by setting a very lax timeout for the maximum, but we can have a very aggressive timeout here. And in reality, there's always going to be things that happen later because, this is a distributed system that we're talking about, and therefore things will not end when they should. There'll be timeouts, there'll be JVM stalls, and all this sort of thing. That's just reality of where we live. But you can still put all of these things into the event time semantics of Flink very easily. And so it's very easy to actually construct a process function that naturally expresses the flow of a trace as it goes throughout Airbnb's infrastructure. So that is the basic of the job. And I went through it super fast. I hope that you at least get the idea of it. And we've had some pretty good successes along the way, and we've had some big learnings, most of which are shared by other people here. So the big thing is that it actually works. We're processing about 3 million events per second through this job. And with that, we're reconstructing a significant fraction, as in the vast majority of requests that actually come into Airbnb's infrastructure. We are reconstructing the full trace and able to compute statistics off of those traces and sync those to the downstream vendors and choose which ones we actually keep. So we can keep every trace from an employee at Airbnb. We can keep the vast majority of unique looking exceptions that happen on various different services and make sure that when someone actually sees an exception, they can go into the tools and see the same exception in every tool. And then we can add links between those, which is something we're still kind of working on. The second big thing is reuse of data. And this is actually a really big thing for us because in a very much earlier iteration where we were building a stateless stream processing version of this that analyzed SQL queries, we saw that once we had the data, teams like security wanted to use it. Our core storage team wanted to do more advanced analytics on it. We actually had some other somewhat random requests for this same data. And so we really want to make sure that when we built this, there was an opportunity for reuse of the data kind of built into the architecture. And so that was one of the key decisions in terms of going towards a stream processing view of these data. And so what we've actually found is beyond this kind of trace view of things where you see, one service calling into another service, calling into another service, and so there's 6 services kind of represented in this short graph. Time is on this axis. The service calls are on the kind of the vertical axis. You also have the ability to feed this into tools like Druid. And so we have a high dynamic range histogram implementation in Druid. And so if you've watched anything by Gilteen, the nines matter. And so we're able to have histograms that go out to 4 or 5 nines. So you can actually start to see GC pauses. And you can see that most of the time this green endpoint right here, it's below 20 milliseconds. But once you get out close to 3 nines, and I'm only showing 3 nines here because it's only what I had in the default view. Once you get out to 3 nines, it's up to over 100 milliseconds. And if this service is called, 50 or 60 times in certain asynchronous jobs or that sort of thing, that starts to matter. Tail latencies matter. And so providing these sorts of summary data has been really helpful for especially more data storage layers of the infrastructure. And so we finally get away from this siloed data view of the world and start to break those silos down. Another success we've had is actually having this post-sampling of data. And that's, as I've already kind of mentioned, being able to decide which data to keep after seeing all of the data, but not having to store all the data for anything more than a transient period in Kafka. And so we can have really aggressive expiration in Kafka and just kind of use each of these layers almost as a routing layer with very small transient state. And then, obviously, when you have a stateful stream processor and you have Kafka, my actual staging job and that sort of thing can just be reading off of production Kafka, a subset of the partitions there, and it's very natural to have these sorts of staging processes. And we're at Flink forward, like it's not novel to do this, but having this ability within a distributed tracing system is actually a very nice property to have. And so one of the difficulties we had, which will surprise no one, when we hit high scale is serialization. And so we was just spending all of our time serializing. It was at one point, it was 80% of our entire cost of our job. And that was because we were doing some rather silly things. One of them was we had some polymorphism in our Podro. And once you get polymorphism, you have this nice switch statement that has to happen, or if statement that has to happen, and you have to check things and all this. It just slows everything down. And so by embedding those decisions of the Podro into Cryo and kind of doing that sort of thing, we were able to get a 3x performance improvement with our custom serializer. I wouldn't expect this across the board. This is partially because of the structure of the data we were dealing with, but it still wasn't great. So you have a custom serializer, you're doing basically the minimal amount of work that you can do for JVM serialization, but we have a lot of strings. You know, people want to tag all this stuff with metadata. You're trying to stick as much data as you can onto each of these events, and that's just a lot of strings. And if you actually look at all the strings and deserialize them into Java objects, there's no way around it. You need to reformat them because you have 16-bit characters in a Java string. You can't just have a flat buffer that you're looking at if you want a real Java string. And so that's kind of a problem. And so it's still actually a significant fraction of our CPU cost, and that makes us so that our job is actually CPU bound, even though we're just kind of serving as a routing layer. There are obvious ways around this. Having an opaque string and a flyweight pattern, so you have a really lightweight object that's just pointing at a byte buffer that you never actually deserialize, makes this a lot faster. It actually improves matters on the order of 5x for the total serialization cost and GC cost. And that's just in like rather simple benchmarks. The last problem that I want to talk about really quickly is there's a lot of coupling between operators. And so what we've seen is this is basically our job. We have inputs, we go to collectors. One job dies for any reason, the whole thing dies, you restart, that's fine. We understand that. If one job degrades though, say you have a noisy neighbor, you have something else, what happens is you get back pressure. And you get back pressure, goes to the inputs, you starve your other task managers, right? And you get back pressure up to the Kafka stream. And now all your downstreams are actually starved. And it's actually worse than this, especially when you're dealing with 3 million events per second, because if your watermarks start to get misaligned, you start to build up state very fast. And so we go from transient state from being tens of gigabytes to transient state being a terabyte in a matter of a couple of minutes. And that's not really something that we want to be dealing with, and that becomes very expensive when you're talking about storing that out to a durable store. And so a lot of the upcoming work around watermark alignment and that sort of thing at the source layer and around rescalability and kind of dynamic changing of the scale of the job is stuff we're really excited about and seeing that stuff work. And one note, this actually got a lot improved after Flink 1.5 and the credit-based network management, but you need to tune that for packet rates a little bit when you first get it. And so we are looking at pre-partitioning the data into Kafka, and so we can have independence at this initial ingestion layer, but that's really tricky to get right. And so, but it basically allows you to limit fan-in. And so if you partition Kafka the same way that you're going to partition this downstream data, you can limit the fan-out. And so the impact of anything going wrong or the impact of this slowing down can be limited, but you have to get that really right because you have to do that really carefully. So next, we want to localize the impact of degraded performance. We want to load shed. As I said, most of this data we want to throw away anyway, but we want to be able to keep the right data. And so load shedding is a natural part of the observability pipelines. And we want to add links between more of the tools that engineers use. I didn't do a whole lot of this work. Nelson Gautier is kind of the person who inspired a lot of this work and inspired me to look into Flink. Jerry Chung is actually the engineer who has built a lot of this in the last 6 months. And the rest of the observability team, we're pretty small. And that's all I got. Thanks so much.
Thank you very much. We are a little bit, I think, over time. So if you have any questions, please ask them Brian offline. Thank you very much, Brian.